Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I am very pleased to welcome today John De Niro from University of California at Berkeley. He's been working on statistical machine translation there for a number of years, and he's about to finish his PhD working with Dan Klein. And rather than just read the title off his slide, I think I'll let him tell you what he's going to talk about.
Great, thank you very much for inviting me. So this talk is about the models and techniques that allow us to leverage the large amount of data that we have to train machine translation systems to get the maximal information out of those data sets. So I like to start by talking just briefly about why we're working on machine translation and what it means for the world. So machine translation is typically considered in three use cases. Assimilation is the case where there's a document that I don't understand that I want to be able to understand. And the primary institutional users in this case are governments who are trying to engage in various forms of intelligence gathering. And then on the other side, there are individuals served, for instance, by Microsoft. Right now, the estimates are that 73% of internet users come from countries where English is not the first language. So this is very important to allow them to understand the English web. Dissemination is the opposite case. I have some document and I'd like to share it with the world. Microsoft, I guess, was an early adopter of this sort of technology. And a more recent example is TripAdvisor, which their primary asset is user reviews about various destinations around the world, which were all originally in English, but now have been machine translated and republished so that they can enter new markets. And I think dissemination is a case where individuals are interested as well. My personal favorite example is called Twinslater. It's a Twitter addition that sets up a twin account to your Twitter account so that every time you tweet, it tweets as well. Very useful. Communication is perhaps the most obvious, but perhaps also the most underserved application of machine translation, where you can imagine there are lots of institutional uses. Some of them, they could even save lives, like emergency room triage. And then there are also individuals, like myself. So every couple of weeks, I talk to my popo in Taiwan over Skype. And right now, I can only say things like Happy New Year. Perhaps with machine translation, I could one day say more. And this is a heavily adopted technology, as you probably know, within Microsoft. But the published statistics are few and far between. But recently in the New York Times, it was published that people are using this service hundreds of millions of times a week. So it's a very practical problem, and we're interested in solving it. And the idea behind data-driven machine translation is that we'll take two forms of data, one of which is examples of well-formed sentences in the target language that we want to generate, and another is a corpus of translations that we've collected. We want to distill all of the patterns in those corpora into a model so that when a new sentence comes in, we can come up with a reasonable translation for it. My work almost exclusively focuses on what you do with the parallel corpus, the example translations. And at a very high level, what we're going to do is carve up the sentence that comes in into pieces that we know how to translate. So we know how to translate después as later. We know how to translate yo lo haré as I will do it. And we're comfortable stitching these two things together because the syntactic type of the constituent that we've removed from the left-hand sentence has been replaced with something of the same type, an adverb. So that's a toy example. Here's a real example from the syntax-based translation system at ISI, which I worked on for a summer. Here's an Arabic sentence that comes in. A human translator says that this should be translated as Albaz declined to make any statements upon his arrival in the province. And the machine translation system gives a similar translation. Albaz declined to give any statements upon his arrival in the province. So a near-perfect translation with syntactic analysis that's quite reasonable to boot. Of course, this is one of many options that the system considered. And the choice of this particular one over all the others was driven by a set of features that we have to learn and we have to learn how to weight them. OK, so that's the very high-level perspective on what machine translation is, which most of you probably know, but I thought I'd represent it. So the structure of the talk is that I'll walk through what I consider the 3 core problems in machine translation and talk about how my work is related to each one. So this is learning a model, applying the model, and choosing a translation. Learning a model says, I want to find all of the example translations I can and distill their information into translation rules, or correspondence rules of how I turn one language into another. And then I'll apply the model in order to figure out, under all these translation rules, what translation should I have for an entire sentence. And of course, because this will be a statistical model, we'll in fact get a distribution over a lot of different options. And it's neither theoretically nor empirically optimal to just grab the top one. So instead, I'll describe a technique where we map all of these different options into some space and select within that space a translation that will be of higher quality than just the one on the top of the list. OK? So let's learn a model. In comes a sentence and its translation. And we would like to learn that thank you means gracias and not learn that thank you means muy buen, even though they both co-occur. And so what we're going to try to learn is a correspondence between the parts of the English sentence and the parts of its Spanish translation. And we can represent that correspondence by saying roughly that these words mean gracias. Now, once you learn this correspondence, you can do a lot with it. So for instance, you can do things like find a syntactic analysis of the English sentence. You can learn from the correspondence that this entire constituent means this entire constituent on the Spanish side. And likewise, that its subconstituent has a coherent translation. And you can learn rules that abstract out subconstituents from full constituents, et cetera. So once you learn the correspondence and you nail it down, you can learn larger rules. But we're really interested in focusing on how we learn the correspondence. One big insight from the early 90s was that, well, we could try to do this with a dictionary. The dictionary doesn't have full coverage of what's going on. But we can learn a lot about how languages correspond based on co-occurrence patterns. So this was established as an alignment task, which is recover the correspondence given many examples of sentences and their translations. And a lot can be inferred from just lexical statistics. So every time I see the word thank, I see the word gracias. But the correct answer here is not the one-to-one correspondence between words. And some cases are very tricky, even for people, even for annotators. If you ask them, example is the word I in English, which is the subject, indicating that this is a first-person sentence. And there's no subject in the Spanish sentence. Instead, the first-person aspect is inflected on the verb. So a professional annotator, if given the option to say, maybe this is aligned here, would often say maybe. And about some of the classical solutions that we're going to try to replace. Well, they were about predicting word-to-word links. And they were driven by learning conditional word distributions. So you'd learn something like, what are all the words that I expect to see co-occurring with the word you? And if gracias is one of them, then I will infer this link. Now, if this already looks suspicious to you, then you're on my side. Because gracias is not a translation of you. So one thing we might want to do is learn a correspondence that looks like this, where all I've done is erase some lines. But what I'm trying to convey is that thank you translates atomically as gracias, as opposed to being decomposed into 2 words. And from a modeling perspective, we would like to say that gracias and thank you should be a parameter in our model. We should learn that these 2 things correspond, as opposed to trying to break them up into individual words. Now, of course, doing this involves a new problem, which is that we have to infer the phrase boundaries for a language at the same time that we learn the alignments. And these boundaries depend intimately on what other language we're trying to translate into. So I wouldn't have carved up the English sentence in this way were it a different sentence on a different language on the other side. So we have some joint problem here, which we'll work on. And a second challenge is that there's additional information in composed phrases. So that is, while we can decompose the structure of the sentences in this way, there's also a very common occurrence pattern of I will do it, meaning lo haré, which is a larger composed structure. It has a decomposition. But there's so much data out there in the world that we can learn things about these longer sequences of words at the same time. OK, so I'll present two models, one to address each of these challenges. If you have questions along the way, feel free to stop me. So the paradigm that we'll use in order to find a phrase correspondence is to train a generative model that explains the observed translations by some latent structure. And that latent structure will correspond to a process where we assume that phrase pairs are generated independently. So as an example, here's a sentence. Here's its translation. This whole thing is our observation. And we assume it came into being because we first generated the words thank you and gracias as one phrase pair. And then we generated a phrase pair with commas in it, another phrase pair with I will do means haré, and etc. So by assuming this hidden structure, we're able to explain the observation that we see. Now, of course, there are many hidden structures that explain this observation, but the paradigm of generative modeling says that we want to explain all of our different translations with some shared set of parameters, and therefore we can learn something that generalizes well from this sentence to other sentences. And I'll explain the details of a model. I'm going to skip some steps. So in advance, know that in the next slide, I will have omitted anything about sentence length and phrase reordering. These issues were, so these are basically the pieces that you need to know in addition to what phrase pairs you use in order to generate the observation, but they're not central to what's going on, so I'll gloss over them for now. OK, so here's what we're going to do. We're going to learn theta, which is a multinomial distribution over phrase pairs. And we're going to assign the probability of this entire structure, the two sentences and their alignment, as a product of the phrase pairs they contain. Or more compactly, as a product of different draws from our parameter theta. And our global objective, which says for all the different translations that we observe, can be the likelihood of all the observed data, which decomposes as a product over all the different sentence pairs we've seen, all the different possible alignments that we could consider, and then each phrase pair within them. OK? So this is a common thing to do in training a generative model. Unfortunately, in this case, it breaks down, because maximizing this likelihood objective gives a degenerate solution, which is that one way I can explain the data is to say that every sentence pair was generated as one large phrase, which is great for explaining what's there, terrible for generalization. OK? So what do you do about this? Well, the obvious thing to do from a Bayesian perspective is to add a prior. And that's what we did. So we drew theta from a Dirichlet process that's centered around a base distribution that prefers short phrases. So what's going on in this expression is that we have some base distribution, which is something very simple. It says only choose short phrases over long phrases with an exponential penalty on something very long. And then the Dirichlet process is a nonparametric cache model, which is also quite simple. And what it does is it's nonparametric in the sense that we don't know its complexity in advance. We're going to, with the more data that we observe, we're going to keep specific information about different phrase pairs. And we'll leave kind of some set of the infinite set of possible phrase pairs to be just scored under the base distribution. But some set we'll keep specific information about. And this specific information will take the form of a cache. So I walk through my data set. I'm aligning different phrase pairs to different phrase pairs. And I keep track of how many times I've aligned various things. And then when I go to consider a new example, should I align thank you to gracias? I look both at the base distribution and at the number of times I've done this before. And the posterior probability of generating thank you gracias, given all the alignments I've made so far, has this simple expression, or closed form, which says Z is this event of generating thank you gracias. And I look at how many times I've generated that phrase pair over all of the different phrase pairs I've ever seen before. And then I have some expression which says, what's the probability of generating this versus everything else under the base distribution? Now, the reason this form does what we want is that as we observe more data, we get more information in the phrase pair cache. And that data overwhelms the original prior distribution. So in particular, the magnitude as well as the complexity of these phrase pair cache terms increase while the base distribution stays fixed.
Is this something you do in training?
Yeah, so we're doing training. We're trying to figure out how to align phrase pairs to phrase pairs. Is that helpful?
Yeah, but something doesn't seem quite right about this. I don't know.
So basically, we're using an exchangeability property of the distribution to say, I assume I align one sentence after I've aligned everything else. And that's how I can have these terms in it. Now, you might worry that early on, I haven't aligned everything else yet. And so for this reason, we have to go through and iteratively realign everything by sampling over and over again.
You could also do variational Bayes, right? I mean, I realize it's not particularly efficient because then you need to consider all possible phrase pairs and weight them by the prior, but
Yes.
I mean, you don't have to do iterative alignment. It's just easier to do Gibbs sampling.
Yeah, I think it's just easier to do
Yeah,
Gibbs.
and more computationally attractive.
Yeah, that's right.
So hyperparameter is trained also.
This is not trained.
What do you use for the base distribution?
The base distribution is a geometric distribution on the phrase length itself. So you multiply together kind of how many words you've generated. And then it has some lexical co-occurrence terms as well, just to throw out stuff that's completely unreasonable. Model 1, if you will.
Couldn't you get this by some kind of iterative EM type of process?
Well, it just depends on what objective you're trying to optimize. So if EM is only, if you're running EM to score maximum likelihood, you're going to get these huge phrase pairs that you'd like to avoid. A variational approach like Chris was describing is basically EM.
Yeah.
So yes.
Where you use an approximate distribution kind of like that you incorporate.
I guess one of the other underlying tricks here is that this problem of carving up sentences into phrases and aligning them jointly is an intractable problem, and so sampling is helpful for encouraging tractability there too.
What is C and Z in this one?
So C is supposed to be this cache structure, which is just the count of the number of times I've aligned. Z, which is the type of thank you and gracias co-occurring together. So Z is a type of a phrase pair. And C is the cache of how many times I've aligned things.
So this is kind of an online paradigm where you basically align a sentence according to the base distribution, then you start accumulating stuff in the cache. And when you align the next sentence, you have those counts in the cache.
Sort of. In fact, we start with an initialization of an alignment of the entire corpus. And then we go through and realign each item.
What's C? What's C in that? That's the side. That's the cache.
That's the cache.
So the alignment uses this model, does it? Or do you do separate alignment?
The alignment uses this model. So as we're aligning, we're updating the cache. We're just trying to get posteriors under one global model, which we're learning at the same time.
But as you train the model, you basically don't, okay, let's train the model. Now we're going to align it because you've got the cache. The cache doesn't the cache have everything in it you need out of the alignment?
Yes, everything you need out of the alignment is summarized in the cache.
Yeah, so
which is why we can express the posterior probability of things.
When you finish training,
as a function of the cache.
That's your fun.
Yeah, that will do.
So your alpha and theta 0 are constant?
Alpha is, yeah, a fixed hyperparameter, and theta 0 is a fixed hyperparameter as well.
By the way, where does this fit in with the IBM models? It might be a slightly clueless question, but...
Good question. So the IBM models are word-to-word alignment models.
There's no phrasal model in there.
So there's no kind of phrasal model, and there are no terms in the IBM models that say, here's the probability of some phrase conditioned on some other phrase.
But I assume this fits in with some other work that's currently going on, because I know that people are doing a lot of phrasal stuff these days.
Absolutely. So, but the typical pipeline was run a word-level model in order to fix the correspondence, and then learn phrasal information given a fixed correspondence. And here we're trying to learn the phrasal model. And a lot of work has been done on learning phrasal models as well. This is our version, and it seems to have stuck pretty well. So in practice, you can train word-level models and intersect them in various ways. For those who know a lot about translation, this is Giza++ with GrowDiag final. Gives you some analysis. Sampling from our system gives another analysis. And the word-level models break down exactly where you'd expect them to, where you have multiple word constructions that can't be modeled well as individual word-to-word relationships. Yeah?
Can I go back one more slide? show you keep updating the cache. Is that when you?
Yeah, so grab some sentence, realign it, update the cache by removing whatever was your alignment that you had before and replacing it with the new alignment that you chose under your current model.
You update the cache for every sentence pair?
Uh-huh.
And you revoke its counts from the cache before you align.
That's exactly right.
Part of the example.
So you see, basically, assume that you'd seen everything else except for this sentence. So you remove whatever counts were contributed by this sentence from your cache, realign it, and then add back to the cache whatever counts
And
you
you
observed.
initialize the cache with the GrowDiag final from the word alignment?
That's what we did, yeah. So recent results say you can initialize it with almost anything. Model 1 even.
Isn't the cache a little bit like a model that you're keeping constantly updated?
Yes.
Yes, it's a lot like
How
that.
different is the cache from your actual model that you're learning? Why do you have to have a cache and the model?
Well, consider them as sufficient statistics for the model. So are the statistics in the model the same thing? Well, in the case of multinomials, basically yes. In the case of other things like Gaussians, they're a little different, and this is more like they're a little different. So there's some simple expression relating the statistics that we track and the model itself. Whether conceptually you want to think of them as the same thing or not, well, that's up to you.
Yeah,
But I try to keep them separate in my
The
mind.
problem is that given the cache, and every time if you want to align a sentence, you have to change your cache a little bit to remove those statistics for that. So you
That's
actually, effectively, you have a bunch of models. I mean, for every sentence you have a model.
No, it just needs the bookkeeping.
Yeah, you have a big,
Same way
you
as
have
counts
bigger
come
pool.
from.
You have big pool, a single pool. But for every single sentence, when you align, you just create a specific model for that.
Well, that's the implementation details.
Right. But I mean, the point is what we really care about is the correspondences themselves and not the model. And so that's what we're trying to learn. So what does all this machinery do? Well, it boosts translation quality a little bit. It reduces the number of phrase pairs that we have to keep track of in the end system. So we've reduced the complexity of the system. We've increased its performance. We've also proposed just a simple generative model to explain what's going on that doesn't involve a lot of post-processing heuristics, which is nice because it can be extended in various ways. And that's exactly what's happened. So there's been a lot of work about nonparametric Bayesian priors, consistent sampling procedures, and how to combine them for various different forms of translation that's been going on for the last couple of years, which seems very encouraging to me. OK. More questions on that? We talked about it in some detail, so I guess I'll move on to really recent work, which I'm excited about. So this is what do you do about composed structures? So when we translate, let's say we found this correspondence, we already know that it's important to keep track of composed information. So I've figured out this correspondence, which means I also know how to translate the past 2, or I know how to translate 2 years. And there's an old idea which says that finding this minimal alignment, we should use the composed structures later on for translation. The new idea is we should actually use these composed structures when we're trying to choose what alignment to use. So that is, we want to select an alignment that provides us with good composed structures, ones that we've seen many times before in the data. So we just wrote down a model which predicts this entire analysis. It has features on word-to-word links, like in translated from Zhong. And these come from simpler word-to-word level models. Come from dictionaries, various information sources. And we also have features on phrase pairs. So how many times have we observed in the data this larger phrase pair? And these, again, can come from simpler underlying models. But they leverage the same information about composed structures that we already know were useful for translation and push them back earlier in the pipeline to how do we analyze these two sentences and figure out how they correspond. So in comes a new problem. And here it's kind of deep into the technical content, for, I guess, mostly targeted for people who know something about translation already, but I'll do my best to explain it to everybody, which is that the problem we're trying to solve is that we've observed these two sentences, and we want to find some full analysis of their structure. And we're going to do it in a setting where we only consider alignments that hierarchically decompose. So we want to be able to do this efficiently, which means we want to be able to do some divide and conquer dynamic programming approach to figuring out how one sentence corresponds to the other, which posits things like I'm going to divide this sentence up between in and the, and between Nian and Zhong. And I'm going to align one part to the other part and one part to the other part in such a way that I don't have to consider their intersection. And then I hierarchically decompose it in this way. Now, finding the word-to-word links under this hierarchical structure is something we know how to do because the word-to-word links are local to the green boxes that I've drawn. One of the tricky parts is that the phrase links, these features on full phrases, aren't necessarily local to the hierarchical decomposition, which means that we have to store information not only about how we've hierarchically decomposed something, but also what alignment decisions we've made on the perimeter of the regions that we've decomposed. So we developed an agenda-based coarse-to-fine parser, which basically finds these alignments, scoring both word and phrase features, using a state space that tracks peripheral alignments. If you're familiar with translation, this is a lot like augmenting Hiero with a language model. Keep some context around to make your decisions. There's something about learning here, which is that we have to figure out what to do with all these features. We do this with supervised data in an online learning fashion, where our model makes some prediction about how things align. And then a human comes along and annotates what the right answer should be. And in the event that they say the maybe aligns to this translation for past, we interpret that as saying there are lots of different phrase pair options that include the as an optional complement to the noun that it modifies. Which means that we've done something wrong here in our analysis relative to the human annotation. We use as a loss function the number of different phrasal translation or composed phrase pairs that differ between what we predicted and what we should have predicted, and use an online learning scheme to adjust the model parameters so that we prefer the gold over the guess by a margin of this loss function that we've introduced.
So those are the red ones there?
Yeah, so loss would be 3. And here we compared it to an unsupervised word model baseline based again on the IBM models and some heuristics on top of them. Supervised system that was a phrase-to-phrase system but did not consider these composed phrase pairs that we worked on last year, which I haven't really described. But that's basically the effect you get from just introducing phrase-to-phrase correspondence and supervised data. And then the rightmost bar is the fully composed phrase pairs. So now we're considering larger structures at the same time that we consider smaller structures. And here we see benefits both in the alignment quality relative to what a human would predict and in translation quality. And this was true across 2 different translation systems. For those who are interested, we put it into Moses and Hiero. Joshua. This is from Hiero, yeah, from Joshua. Okay? So some takeaways. Large data sets they're large, and so they can provide statistics about multi-word phrases in addition to individual words. And nonparametric models are useful for handling that increased complexity by selecting which phrase pairs to pay attention to as we process the data. And the more context we incorporate, the better we do. All right.
A little bit more about that context. You kind of flew right over that. So in the alignment, you said you were using alignment contexts.
So all I mean by context is that when I make a decision about to align this to this and this to this, I also consider a larger structure that consists of both words at the same time.
Well, you made this analogy of combining Hiero with an LM, and I wasn't sure what that analogy.
That's merely an algorithmic complexity that doesn't really have anything to do with the modeling, I guess. All I'm saying by context is, should I align 2 with Liang? Well, maybe I should think about what it's 2 of, years, in addition to kind of the word previous to it when I make that alignment decision. So I should consider features on this larger box in order to decide whether to add that.
So the analogy, if I understand correctly, the analogy with adding language model context to, say, a synchronous grammar encoder is that you know, if you have really long sentences, the size of these blocks can get arbitrarily large, but the context you have to remember is limited by the maximum size of the phrase pairs.
That's exactly
you're
right.
Considering. So if you have, you know, if you have a block that's, you know, n by m, but you have phrase sizes limited to k words, then you have to keep track of a k-1 word perimeter of your larger blocks.
Yes.
And that's the analogy to the extra language model state you have to keep track of.
Yes. Okay. So
Does that make sense?
Yes, thank you.
it's maybe lost on everybody but Bob. But, but all I mean by context is that you should consider larger structures when you align.
Can I, sorry,
Yeah.
I don't mean to drag you down, but one more question. So the minimal phrases are highlighted here in blue. Those are the things that are learned by your model.
Uh-huh.
And then do you also extract larger phrases and then stick those in a fixed phrase table and decode with them?
So we're only using this model to learn alignments.
Yeah.
What you do with those alignments,
So
we're agnostic about, and we've basically just allowed other people's systems to process the alignments.
Agglutinating heuristics.
Standard,
all that
agglutinating, high-row extraction, whatever you want.
stuff. Okay. And these Myra features, are they used at runtime or not at all? That's
Not at all.
Again, totally independent. Just
I mean, they certainly could be, but all these improvements that you're seeing are simply just from putting different alignment grids in.
Yes. Okay.
Okay. Let's actually translate something. So we're going to translate mi dormitorio nuevo no es ni grande ni pequeño. If you don't know what that means, you soon will. I just want to give you a flavor for what a synchronous context-free grammar can allow us to do in translations. They can allow us to encode vocabulary. So we can know that dormitorio means bedroom. Here's some more vocabulary, various adjectives from this sentence. And as we apply these rules, we're building up sub-translations. So translations of subsequences of the original source sentence that we want to translate. We can also encode reorderings, such as that nouns and adjectives need to reorder. And we can encode larger constructions, like this neither nor construction in Spanish. And by applying this rule, we can stitch together all of the sub-translations that we've built into one full translation of a sentence. This is the kind of formalism that we're using in order to translate.
Does this mean that you have to have kind of parsers in both languages?
In fact, what we do typically, so for instance, in the original example that I showed you early on, is you only parse the target language. You project, effectively, that grammar onto synchronous derivations through the correspondence that we've learned. So what happens if we do this in practice? Well, we learned one of these grammars from 220 million words of Arabic to English. We then threw out all the rules that don't apply to a sentence. And what was left for a 30-word sentence was 332,000 rules of various sizes that all apply to one particular sentence and may apply in multiple locations in that sentence. And so what I mean by a size 8 rule is something that has 8 objects in the source size. So we have this big grammar. It turns out that for every one of these large, what I'd call large context rules, rules that cover large portions of the sentence and have many elements within them, you can also build the same structure using smaller rules that also exist in the grammar. So the problem with using these smaller rules is that they don't have as much context in order to make a translation decision. But they have the capacity to build the right structure. They might just not have the features available to tell you which one's the best translation. So I've worked on coarse-to-fine translation, which is a way of speeding up the translation process under these very large grammars. And the way it works is that we apply only a subset of the grammar that has small rules in order to get these very articulated structures. From this, we only keep around the information that certain constituents or certain spans of the original sentence shouldn't be translated. So for instance, we prune away that the idea that nuevo no es ni is something that we'd like to translate. And then when we translate under the full grammar, we ignore the possibility of translating this subsequence. In addition to some optimizations and grammar transformations, this coarse-to-fine approach gave us 5x speed up in the largest translation grammar we could find, the one that's used at ISI in their syntax-based translation system. So I guess the takeaway message here is that if you want to exploit large data sets, you're going to end up with some very large search spaces. And I think coarse-to-fine inference is a powerful technique for doing so, basically iterative refinement of your predictions. Questions?
I'd just like to make a comment. I love that example because it gives a possible answer to something Chris and I were debating last week. If whether we were talking about it in the context of a model that actually uses all possible phrases consistent with the derivation of the Sinhui paper. You know that paper.
I know it well.
And we were, and I was making the argument that, well, if you're doing that, you actually should just let the minimal phrase pairs drive the translation, because that'll reduce the search space and you'll find all the others anyway. And Chris was making the argument, yeah, but if you don't look at some of the big ones, you might have a sort of a dip in the projected score in your search, and you might prune out something that was partially constructed according to the minimal phrases, whereas if you applied the big phrases, you would kind of jump over that potential well, so to speak.
And this kind of stuff happens.
And this seems to be the obvious answer. Do it in a coarse-to-fine fashion, where you use the minimal phrases first, prune out the real losers, and then go back with the larger ones. So I like this very much.
So my understanding from this is that you're using syntax information in training time, but probably not in test time, depending on what the model is. Is this right?
What we do is we use the syntactic information in order to form a translation. In the sense
So
that
it's in decoding phase.
this is the decoding phase.
Okay, fine. But so that source of information is different than the one you use in the training, which.
Yeah.
So you can use that in the same way.
In fact, the version of training that I described didn't use the syntactic information in order to find the correspondence. I've done other work that does, but there's only time to present so much. So the most typical scenario is that when you're learning correspondence between languages, you ignore the syntactic information in order to do the alignment. And then once you have an alignment there between the words or the phrases, then you layer in syntactic information.
That's a little bit counterintuitive in terms of
certainly,
machine learning.
certainly.
Using consistent information between training and testing.
Certainly, and like I don't mean to advocate this approach. In fact, I advocate the opposite, which is that we should integrate all of these decisions into joint problems. You just happen to have caught the entire community at a point where we're still transitioning into larger joint models.
And how universal is it to use syntax at all in these translation systems?
I think it's now accepted that there's some benefit from it.
So what percentage of people are using it?
Not 100. So I mean, there are existing systems. Like if you use Google Translate today, there is very little syntax involved in the decisions that are made. Although in-house, they've committed to developing systems that include syntax. Here,
I'm going to make up some statistics.
Oh, yeah, good.
I answered Dan's question. I would say that it's like 25% using explicit syntax, like noun phrase, verb phrase. 50% using the as the phrases become adopted by some people in the field, formal syntax, where you don't actually have a parser, but in learning you impose a hierarchical structure on the word alignments and implicitly learn a grammar that way, and about 25% still using no syntax at all.
It sounds reasonable to me.
And there is a difference whether you use the syntax on the source or the target site.
Yeah, so there are in fact dozens of variants of these kinds of things, but syntax is a popular thing to include. Okay, last step. I told you that if I take an input sentence and I push it through my model, it will give me lots of different options and a distribution over possible translations. And sometimes the best one is not at the top. So in particular, we can plot. On the horizontal axis, we find the model score for an aggregate of 1,000 different sentences. And on the vertical axis is the translation quality. So this is a comparison to a human translation, how much overlap there is between the two sentences. And we find some reasonable positive correlation. It's not perfect, but at least it's the case that higher model scores correspond to higher translation quality. Unless we sample from near the top of the distribution. So the best things that come out of a translation system. There isn't much correlation at all between translation quality and model score. And in fact, the highest scoring translation from this data set sat in the middle of this cloud. So we'd like to do something to help us take the output of this model, which is very good at figuring out what's really bad and coming up with stuff that's reasonably good, and choosing among this cloud a translation which is particularly good.
So this is comparing the one best output to n best output?
This is for each of 1,000 sentences, I have sampled from the distribution.
Okay, so it's not the n best, it's a sampling over the entire distribution.
Yeah, of the proof space that's left over from a decoder.
Right.
The plus is sampling over the entire distribution.
Right. And the x's are the one best.
X's are
No, all of those are samples, except for the diamond is the one best.
Oh, okay.
X is a sample of the top 5 or top 10 something.
Yeah, so the way I'm getting different samples is I'm skewing the distribution toward the one best, or I'm skewing it toward a more uniform
with
distribution.
an exponential one.
I see. Okay. All right.
Okay. So what do? Took inspiration from Tolstoy. Happy families are all alike. Every unhappy family is unhappy in its own way. How does this apply? Well, I figure if we average over different sentences, we might find the phrases that are alike and consider those to be the happy phrases. Of course, you can't average over sentences. They're structured objects, sequences of words. But we can average over a featurized representation of them. And in this case, we'll just use the count of the words and phrases that they contain as a representation for the sentences themselves. So we re-represent each option. We have this distribution that comes from the model over the different options, which allows us to compute the expected output, which tells us that the model, as considered as a belief distribution, would like to see do it appear 0.54 times in the output. And then we choose a sentence that's similar to this output in some way. So this is a very simple procedure. The problem is that there are many, 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 many different options. And summing in this way is linear in the size of the number of options, which is actually too slow. So the interesting part of this work is how we compute this expected output from a compact representation of the entire translation space of reasonable translations of this sentence. So we want to encode the distribution, and the way we encode it is with a hypergraph where the nodes are partial translations. So they're translations of contiguous subsequences of this sentence. So I can translate yo as I, and I do it by applying this rule. And similarly, I can translate lo are as shall do it. Some translations of subsequences involve composing rules together. So I've composed this translation for way to translate lo with this way to translate are. And when I do it, the important observation to make is that by gluing these two rules together, I've generated the two-word phrase do it in the output. And likewise, when I combine I with will do it, I generate I will and I shall. Here's the important part, which is that we can collapse the representation of different translations into one node, because regardless of whether I say I will do it or I shall do it, combining this with later provides the same bigram, the same two-word phrase. So we build up these structures which implicitly represent the entire space of translations that we're willing to consider, and that gives us an exponential reduction in the amount of space we need in order to encode this long list of options, and kind of running algorithms over this structure can give us big speedups in the amount of time it takes to compute that expected output.
How is this different from the inside-outside algorithm?
It's not. So once you build this structure, you run inside-outside in order to get posteriors on these rule applications. And then your total expected count for the word do it is a sum over all posteriors on rule applications that generate the word do it. So I guess it's there's one additional step after inside-outside, because you want to sum over all the edges that are equivalent. So here, this was work I did at ISI on their, these are results from their hierarchical translation system. And you see some small benefit from running this consensus procedure on a list, but if you run it on the whole forest, you get much more benefit. So more recently, we've been trying to use this same idea in order to group or to take multiple models that each have different opinions about how we translate and combine them together. So each one of these models can generate some space of possible translations. Therefore, each one can generate this expected output vector. And we can use all this information in order to come up with a translation. Now, this seems like a very complicated structure. Who knows if we'd use it in practice? But I think it's worth pushing the envelope on terms of how well we can generate sentences using all the information we have available, which might be factored into different models. OK, so for those of you who are particularly interested in this kind of system combination approach, I'll give you a quick FAQ on what we actually did. So we combined different models using a linear consensus model, which has features on which model we used, which kind of underlying model we used, expected counts from all sorts of different models, the model score from the original model, and the length. And we only considered output sentences within the union of the output spaces of all the original models. So you consider all the different things that individual translation models will do, union those together, compute some consensus score over all of them, use some phrase statistics, which are expected counts, or phrase posteriors. They're both equally effective, and you get some amount of benefit. So this was on Google's full-scale research translation system from Arabic to English, relative to their best single system, kind of choosing the thing that scored best under an individual model versus using consensus techniques and bundling multiple models together. You see a substantial increase in this automatic metric, the blue score.
I think it's interesting, the set of hypotheses you consider, because in a more conventional system combination technique, you might take the 10 best outputs from each system, but then you recombine them to get more possibilities. Here, you're not considering any possibilities that aren't generated by one of the systems, but since you're generating it from the entire search lattice, you're considering far more of those.
That's exactly right. So now we have, instead of 10 from each, we have 10 to the 40th or whatever, some huge number of options. And that this is a large benefit relative to a single system model-only baseline. It also provided a small benefit over a more conventional system combination technique.
So curious, when we go back to that formula, I would think that model score probably carry most of the weight. Is it true?
Yeah, the underlying models are very useful. That's why we translate with them in the first place. So,
the impact from the WP.
So all we're doing is allowing a second model to influence the choice under kind of model B and model C can influence the score under model A, as well as the consensus expectations under model A. We all push them all into the same model. This is very important, but these expected counts matter.
Do you have to do any sort of normalization across the different models to make the model scores comparable?
So some of that lives in here. I guess it's hard to dive into the details, but basically you can add a feature on each model, which allows you to in some sense, reweight the whole thing. And
it's a bias and not a scale.
Yeah, this is a bias and not a scale.
Yeah. Do you want a scale factor too?
Yeah, maybe.
It's
hard to get.
Typically we train these models using some sort of optimization that doesn't look at this doesn't look at the scaling of the weights. But we know if you want to turn those model scores into probabilities, then you have to include a scale factor which controls how sharp the resulting probabilities are. And I would think that when you're combining, scores from different models, that implicitly that scale factor, which in our standard training procedure is uncontrolled, would end up influencing how those model scores combine. If you have one model that happens to have kind of the weights weighted so that you get kind of flat distributions, and another one that has very sharp distributions, the one with it's going to be hard to prevent the one with the sharp distributions from
the
ones with flat distributions.
I understand what you're saying. So let me give you my opinion, which is that if you're going to run through this large structure, there's some amount of training of each of these individual models. And what you're using this model for is not to generate a sentence, but instead to generate this expected count vector. So currently these models aren't trained to generate good expected count vectors, but they should be. And we wrote a paper about that as well. And in that case, when you train for something that's probabilistic, you get more control over the distribution. It's part of your objective.
You should get real probabilities out if you train them right.
Yes, presumably. That's right.
So a lot of this seems similar on the surface to, Jerfeli and Jason Eisner had a really nice paper last year about computing expectations, first and second expectations over hypergraphs with arbitrary semi-rings. So maybe the underlying method of getting expectations over n-grams is very similar, but the application to system combination is novel, or is there a big difference that I'm missing here?
So this scheme for computing expectations is exactly the same as what was in his variational method. I mean, we happened to publish it at the same time.
That's right.
So,
forgot. Okay.
Yeah. I guess there is a new algorithm, which is if you want the posterior probability of whether I shall shows up at all, as opposed to the expected count.
Okay.
That's actually not the kind of a special case of an expectation semi-ring, and we talk about how to do that. But yeah, certainly that's a general technique that's very useful for this kind of thing. And if you're ever going to train models that do this, then you need that kind of machinery as well.
This multi-system consensus result, how many systems did you use, and what are those systems?
So we used 3 systems, one of which used no syntax at all, and is very similar to what they are currently using for their web-based translation, called the phrase-based system. We used a hierarchical translation system, which, as Bob described, is formally syntactic in the sense that it decomposes the translations into a hierarchical structure, but doesn't use a lot of syntactic information in the linguistic sense. And then a third system, which has been dubbed in the literature as syntax-augmented machine translation, which actually does use parse trees trained from a supervised linguistic resource, the Pentree Bank, as a third system. And syntax augment, if you know the work done, Sashish Venugopal's system. So, I mean, it's interesting that these all share a common code base. They share a common decoder or search algorithm. They use different pieces of information, and those different pieces of information are useful to combine. So my takeaway points are that statistical models do provide distributions over outputs as opposed to just a one best or an n best list. And those things are useful. And in particular, I think we're able to show that leveraging those distributions will improve performance in a setting like machine translation. But if you want to be able to leverage a distribution over a large output space, then you might need a compact representation and process that instead. OK, so now we're going very high level, which is I like large context models. I like nonparametric models. I really like coarse-to-fine as an inference technique. And I'd like to use full distributions and compact encodings in order to capture everything that's going on in the models that we train. I think these are useful points not only for machine translation, but other statistical NLP applications. And so I'll continue working on those. You might wonder, are we done? Well, despite my best efforts, machine translation still doesn't work as well as it could. So I'll just give you a glimpse at the current projects I'm thinking about right now. One of them is to use morphological information or the structure of words when we're doing alignment. We're considering the composed phrase pair learning work that I described, used supervised or hand-aligned training sets, and we're trying to get that to work unsupervised. And I'm also very interested in pushing new information into these consensus models. Once we've already fixed a posterior distribution over possible alternatives, we're already getting benefits by just summing over them, computing expectations. But think of all the additional benefits we could get by injecting new information there. So thanks.
New information.
You have to clap first, then you kind of...
New information being other things you can compute from these distributions or entirely new models?
I think there's room for entirely new models. I think if I had a first-year graduate student who wanted to add some new piece of syntax into a system, I would say, take the hypergraph output of an existing system and rescore that, as opposed to starting from scratch. I think there's a lot of benefit there.
So with these consensus models, I've always wondered, is it better to do a consensus over similar models or over very different models? Because here you've used 3 very different models.
That's right.
And so the benefit to consensus would seem to be as different as possible.
Yeah, I think you want different models. In the particular framework that we consider, they have to be similar enough that they propose some of the same n-grams. Otherwise, there's no ability to share information between the two. So if they were deeply different, it's hard to imagine how they would combine. But you do want them to have different information sources, then you'd expect to get some signal from combining the 3.
Also, it looks like you also need to have stage for score calibration, because different model will have very different dynamical range. Are they automatically taken care of by these weights?
These are probabilities, they're not likelihoods.
Oh, I see.
They're actually
Okay.
just scores.
Yeah.
Yeah, they're kind of all scores. We do calibrate each model individually. By we, I mean
They say
somebody
they're not
else.
probabilities.
And then I took those models and combined them. But I think there is a role for calibration.
You don't expect it's a good copy.
But they sum to 1.
They're forced to sum to 1.
Yeah, first of all.
Yeah, but it's the issue I was talking about of how you scale the weights. You know,
So,
you get them,
but if you
you get them to
check
sum to 1 by plugging them into the exponential
Yeah.
probability model, but
They may not be
you
trained
end up with very
normalized
flat distributions or very sharp distributions according to how big the weights are.
That's right. But I mean, there are techniques out there that actually consider these distributions as opposed to just scoring functions. You know, one of which we've worked on. And in that case, we found there was no additional benefit to fiddling with a scaling factor after you've done the model training. So it is the case that if you consider these things probabilistically from the outset, then you have to do less kind of parameter tuning later on.
So how much better is this model, the combination model, compared with just conventional way of doing alignment and voting?
What do you mean conventional?
I mean,
Yeah, the kind of thing
the
that...
continuous one, I think that's one question. So, given this combination of model which is done in the runtime or in on the fly, all people do that, say each model output best, and the computational dimension is offset, so and get another final optimal final output.
So how much is this better? Well, so we compared it to 2 techniques, kind of a vote on a whole sentence. So you have 3 different outputs. They all vote on each other, and one of them is selected. And then we tried another scheme where you form a word lattice of sorts and choose a path through that based on some voting metric. And both of those, I think on this data set, they were 0.2 lower or something like that. So you can get similar benefits from a more conventional method. This actually requires less computation in the sense that in order to get that benefit out of the computational method, you still had to do all of this work. And then from each of these, you had to get a sentence. And then we combined each one of those sentences. So you still have to do all the work in the conventional method. and then a little bit of extra work to get a sentence out, and then combine those sentences, it seems more streamlined and, in fact, slightly less computation in order to just generate these expected outputs and then combine all of those.
How complicated? I mean, you have to run 3 decoders at the same time in one machine. In terms of
not necessarily in one machine, but you do have to run 3 decoders, which I guess is true for any system combination.
So going back to the first part of your talk, learning the model, that's a generative model. So I just wonder whether is there any work done on using discriminant training of the model parameters?
Good question. So I told you about two models, one of which was kind of phrase-to-phrase alignment, and that was a generative model. The second thing I told you about with these composed phrase pairs was actually a discriminative model. So yes, there's work on that. I mean, Bob has done some of it as well, and others. So yeah, I mean, it seems like the best way to match human annotation is with a discriminative model. Certainly.
Human annotation is not universally agreed upon.
Very much not. Yeah.
That's a difficult issue for us.
Certainly.
It doesn't necessarily lead to better translations.
Not always. Though we're finding that in this particular discriminative setting, we got some nice benefits in the overall translation.
But you can't really say, is that because your discriminative training method was better or the human annotation was better that you're training towards?
You can't say. Yes?
I have a question. So one of the future work you mentioned was using morphology for alignment. Can you be a little more specific about what kind of things you're doing? Or where do you think it comes?
Sure. So we're just publishing some kind of proof of concept work on this, which says if you take one of the classic models, the IBM, or I guess it's not technically an IBM model, but the HMM alignment model, which says I'm going to align words to words using distributions that say, what's the probability of generating you given gracias, or something like that. And they're driven by these parameters. Well, one idea for using morphology is to say that parameter, which is you given gracias, should have some structure to it. It should have some feature-based representation, which looks at the characters in the word gracias, the characters in the word you, morphemes, whatever you want to pull out of there, and cast that parameter as a linear function of features in some exponential family form so that you can include additional information, prior knowledge in the form of just writing down feature functions. And then train that in the same unsupervised way. The algorithms don't really look different, but you're allowed to inject things like if I see this particular ending on a verb, which corresponds to the first person, and I see the word I, there should be a particular potential to that, which couples the parameters for every verb that's inflected with the first person to all be kind of corresponding to the subject I in English. So we got some benefit in kind of a small-scale experiment on an older model with this kind of technique, which is just replacing multinomial distributions with feature-based log linear distributions. And you know, the jury's still out on whether this will work at large scale, whether it'll work in more of these interesting phrase alignment models, et cetera. Just at the alignment level. That's all we tested so far.
Did you use as a baseline chopping off the last 4 letters of every word?
We did beat that baseline, apparently.
that way of dealing with morphology beats the standard.
Absolutely, absolutely. Yeah. So I think basically when we're learning large distributions over words or phrases, the parameters of those distributions should be able to look inside the object that they're generating. And that's why I see there's a role for morphology. I mean, I think there are many more roles for morphology, but that's the one I'm exploring at the moment.
Yeah, because I think that the role is maybe larger on the generation side rather than alignment side, because I mean, like agreement, this kind of phenomena is on the target side, not on the source side. So rather than learning that kind of thing from the source side, you want to be able to do that on the based on the generated.
Yeah. So I guess that would fall in my final bullet point here, which is that if you're going to enforce agreement in translation, it seems fine to me to do it at the end. Generate some space of the many, many billions of reasonable options, and then rescore that space for things that agree. And if that requires non-local features, we're still in a small enough space computationally that we can enforce that kind of thing without worrying about pruning errors.
For the model you talk about here, how is it possible to deal with sort of fuzzy data, the parallel data, which may not be accurate?
Yeah, I guess every parallel set we have has a lot of noise in it. There are we're assuming that some sentence in its translation are what we're analyzing, but in fact, it's often the case that we have some sentence and a translation with additional information or missing information, or we actually think that this is a sentence in its translation, but this is actually not the translation of this sentence. I mean, these kinds of issues crop up all the time. I think that the unsupervised modeling approaches we use, which are based on very simple processes, are somewhat robust to these issues, in the sense that we include in our models things like. So the supervised learning model is really a semi-supervised extension of an unsupervised model, in the sense that it's not trained on a lot of supervised data, and it's using predictions from unsupervised models, which hopefully were robust to the noise in the data in the first place. And it uses them as features. Good question.
Okay, well, thank you, John, for very interesting.
Sure.